Hi, this lecture is about wave functions. And the wave functions typically are symbolized by this symbol psi. And sometimes we'll have a wave function that is a function of space and time. In this particular case, it's just a wave function that varies over one direction, picked to be the x. But it could be that a wave function varies over x and y, or x and y and z even, right? So we could have multiple space dimensions. And sometimes we also include the fact that the wave function can vary in time. But sometimes, honestly, we can talk about what are referred to as stationary wave functions, or wave functions that don't depend on time. But the example that I have during this lecture is going to be one that's one-dimensional, so just an x, and is also going to vary in time. And this is an important comment right here. A wave function represents all possible knowledge that one can know about a system. It's sort of like the idea is it's the most efficient way to encapsulate all the possible details about a system, a quantum mechanical system. But on the face of it, psi on its own is actually not that interesting to look at, unless you sort of build up a lot of intuition about what the shape of psi tells you about, right? And how that wave function might vary in time. But the point is in order to get to really understand how to use psi, you have to know, what are you allowed to ask, right? So there are questions that you're allowed to ask in quantum mechanics, but there's also questions, that you can ask in quantum mechanics, but there is no sensible answer for them. And that, you might say, is where the breakdown of classical physics happens. It's where the classical questions don't have any meaning in the quantum mechanical world. So another thing is not only do you need to know what you're allowed to ask, right? What are all the possible things that you can ask? And there's lots of things you can ask. But you have to know how to ask it. How to ask it, I'm going to put in a different lecture video, the lecture video after this one. Also, once you get an answer, so let's say you figure out how to ask this wave function what the value of something is, you have to then know how to interpret the answer. So it's kind of cryptic. It feels cryptic at first, but after doing lots of problems, you sort of get into the swing of, essentially what kind of thing is quantum mechanics? Like, what kind of thing is quantum information? All right. So the first thing that we're going to do is basically, actually, let me not say the wave function. Psi is associated with probability, right? So that's what psi can be associated with. Probability is something that people know how to measure, right? The way you measure probability is you simply do something over and over and over again, and you collect data about the outcomes. But the idea is you have to do it many, many, many times to get good statistics, essentially, is the way people say it, right? Just getting one experimental value is not a determination of the probability. You really need to know, how do the possible answers spread out? Like, what are all the possible answers, and which of those answers show up most, and which of those answers show up a little bit, and which possible answers never ever show up, and then you start to build what's known as a probability distribution, like a distribution of likelihood over the possible answers. But essentially, psi it's associated with probability, but psi itself is not probability. Okay, so for fun, let's have a toy wave function to play with, right? And so wave functions, they tend to be, the interesting wave functions that are fun to play with are local. That is psi of x for x far away tends to 0, right? So that's the sense in which it's local. If you go really far away on the x-axis, the value of psi goes to 0, and if psi is associated with probability, you would say there isn't any probability for far away x values. Only for local x values is the probability something interesting, right? So that's what it means for your system to sort of be localized. And so I have an example wave function that's actually not really very physical. That is, I can't imagine a system that it's associated with, but it is something to play with to give you an idea of what the wave function means, right? So here is a toy wave function. And in particular, this is one-dimensional, only depends on the x direction. It's independent of y and z, but it also depends on the time. And I'm going to define this thing piecewise. So for x values that are in between 0, let's say greater than or equal to 0, but less than a distance called L, we're going to say that the wave function psi is some constant times e to the minus I e t over h bar. So necessarily psi is complex valued, right? Remember, using Euler's formula, this exponential is actually a mixture of real and complex parts. So this wave function is a mixture of real and complex parts. And then, so that's only on this interval along the x-axis. But here's a different part of the x-axis. So this is values less than 0. So these are negative x values, but bigger than or equal to negative L. So it's the same length scale. And so we're talking about localizing from negative L up to positive L. Actually, let me clear this up a little bit. So from negative L up to 0, we're going to have a different wave function. It's negative a over 2 e to the minus I e t over h bar. And then we're going to say that for other x, right? So these are x's outside of the interval from negative L up to positive L. For all the other x's, we're going to set psi equal to 0. That's the localization. So there is no probability for the other x's, is the idea. Okay, so here's the idea. And this, I might say, is the main idea of the lecture today. Psi of x and t is not probability, but it is associated with probability density. And I'm going to say it kind of loosely. It's the square root of probability density. Often, psi is referred to as the probability amplitude, right? But there is a sense in which there's a square root. There is a sense in which there is a density. And so here is the main idea. You remember that if you take z, where z is a complex number, and you take its complex conjugate, if you multiply by the complex number, so z star z, what you're guaranteed is this is strictly a real number, and it is strictly bigger than or equal to 0. So this is beginning to look like a possible probability. And that is how we're going to understand using psi. So we're going to say that you can take psi star, which is a function of x in time, and if you multiply by psi, which is also a function of x in time, this thing, if you multiply over a small distance, right, a calculus distance, this is a small amount of probability. This is a calculus statement for the meaning of psi star psi. That is, this thing, if you think about it, is probability per unit length. Because if you multiply by a length, you get probability. And this is the meaning of psi. So psi, if you take it psi star psi is probability per length, then that means in this particular context that psi itself must be the square root of probability per length, where the square root is over the whole quotient, right? So that's the sort of dimensions, right? Sort of the physical dimensions. Probability itself is a pure number, and it's restricted to values between 0 and 1, right? Length is a physical distance. And in this case, we have a probability per length because we're thinking about the probability only varying in one direction, right? Okay, so with our toy model, this is our toy model. Let me rewrite it down here. And what we're going to do is let's practice what's called, so this word is supposed to be practice. Let's practice normalization, right? And this is a typical problem that you have to solve in introductory quantum mechanics classes. And actually, in advanced quantum mechanics classes too, because probability is a normalization thing. So what normalization means is the following thing. It means that if psi really represents probability, then that means the idea is if I were to ask, what is the probability of discovering the particle somewhere between negative infinity and infinity along the x-axis, the probability, if there is a particle, has to be 1, because this is the question of what's the probability of discovering the particle anywhere, right? And it needs to be 1. The probability is 100% to discover the particle anywhere, right? So this is called the normalization condition. And our wave function has a normalization factor, and I called it A. This thing right here is the normalization factor. Let me erase that second tick mark. So A is the normalization factor, and it appears as sort of a common scale in the psi direction. L is the localization scale in the space direction. And capital E is actually it's E over h bar, Planck's constant in here. E over h bar represents some sort of scale in the time direction, right? It turns out that E over h bar has units of inverse time, like per second. It's like a frequency, right? E over h bar. So it turns out that capital E, the kind of values that fit in there, the units, are energy units. So the thing that fits here naturally is an energy. More on that later. Okay, so we need to discover what is the value of A such that our wave function is normalized. That is, what's the value of A that makes psi a meaningful probability amplitude, right? So what we have to do is we have to actually do this integral with this wave function and solve for A. So let's do that as an example. So let me rewrite psi. Oops. So psi of x and t is this piecewise defined function. It's equal to a e to the minus I e t over h bar for x between 0 and L. It's equal to negative a over 2 e to the minus I e t over h bar between negative L and 0, and it's 0 at other x values. So we know that we want to normalize, so 1 equals the integral. The integral goes over all the possible x values, that is everywhere on the x-axis, and we want to do psi star psi dx, right? But psi is only non-zero between negative L and L. And in fact, between negative L and 0, right, it's got this functional form, and in between 0 and L, it's got this other functional form. So this piecewise definition for the wave function, when I integrate over all the possible x values, what I imagine doing is integrating over the pieces where the definition of psi is different. So from negative infinity up to negative L, I'm going to integrate 0 dx. And from the negative L up to 0, I'm going to integrate psi star psi this way, which is negative a over 2 e to the minus I e t over h bar, right? So this is, I have to complex conjugate it and then multiply by negative a over 2, right? So psi, e to the minus I e t over h bar again, right? But then that's only half this interval from negative infinity to infinity. So let's finish. So plus the integral from 0 up to L. You notice that I always go from the lower to the upper, right? Because I need to respect the order at which I'm moving along the x-axis. So 0 up to capital L of psi star psi, but now psi looks like this instead. So it's a e to the minus I e t over h bar. I need to complex conjugate multiplied by a e to the minus I e t over h bar, right? And I'm forgetting dx's, so there's a dx. There's a dx here. And then I got to finish. I can go from L up all the way up to infinity of 0 dx. So you can see that this integral here doesn't count. That's part of the localization of all of our probability. And this doesn't count, right? Because the integral of 0 dx over any interval is going to add up to 0. But this one and this one are not 0. So let's figure out what they are. Okay, so this first integral, right? So now we've got a problem that 1 equals the integral from minus L up to 0. And so this constant A, the normalization constant, it's A star A over 4 times minus 1 squared. So A star A over 4, that's the prefactors. But then if you look at what happens with the complex thing, right, we know that the complex stuff needs to go away. So the complex conjugate is going to take this I and give it an extra minus sign. So that means this minus sign is going to disappear, right? That's the effect. But when I product this exponential and this exponential, these two exponents are going to cancel each other. I hope you can see that. And so the exponentials are gone, and the only thing left over is dx. And then in the second integral, exactly the same thing happens with the exponentials, but the prefactor is capital A and capital A. So the second integral goes from 0 up to positive L of A star A and then dx, right? So this is interesting. A in general is complex. There was actually no reason to suspect that A wouldn't be complex, actually. So let's keep going, though. So I've got, right, the other two parts of the integral that went out to infinity on either side of L, right? Those were 0. And so this is my normalization condition currently. And these are pretty easy integrals, right? So A is not x-dependent. So that means that these things can come outside as constants on the integral. So you can take them out. And then when you finish the integral, it's just going to be this is what you get from the first term, and this is what you get from the second term. And this adds up to a total of 5 over 4 L A star A. Another way to write A star A is 5 over 4 L A magnitude squared, where it's understood that A can be a complex number. So when you solve for A, right, because that's the whole point, we can solve for A this way. So solve for A squared first. So the 4 comes up top, 5 goes below, L goes below. And then the A squared is the only thing left over. And so this leads us to believe that, for example, A equals square root 4 over 5L is an answer. And this is an answer if we assume that A is real. But actually, it's a little bit more interesting than that because A can actually carry any complex phase, it's called. And so actually, A is equal to square root 4 over 5L e to the I phi, where actually phi is undetermined. But the truth is whenever people ask you to do this in classes like this one, you can give, in general, you can give just the real answer. And the real answer, because phi is undetermined, let's just choose phi equals to 0. And then you're just left over with the real part, right? The normalization condition, there is no way for it to tell you the value of phi. And actually, that's a really interesting thing in quantum mechanics that you might study in your future if you stay in physics. It's called the phase invariance of the normalization or something, I don't know, whatever. But anyways, so this right here is our answer. We're just going to assume that it's real. We'll just assume the value of phi is, we can choose it to be 0 because that's the simplest one. And so let's just go that way. So now we can update our wave function to really represent probability amplitude because now it's normalized. But let's look at psi for a second. So let's graph psi, right? So if you look at it, right, for positive x's between 0 and L, I've got the amplitude A. But for the negative x-axis part, it's only half as tall, but is negative. So it kind of looks like the following thing. So let's graph it. This is just a picture of psi. So psi is got this constant value if you go up to L. So this is the x-axis. This right here is the psi of x-axis. And if you go over to negative L, it looks like this. So it goes all the way up to A, but only down to negative A over 2, right? So it's lopsided. You might say that because psi is bigger on the positive x-axis, it's more probable for x being bigger than 0. That is, if you were to make a quick measurement of where is the particle, well, it's more likely to be on the right-hand side, right? So where is the particle? One thing you can say just by looking at psi is it's more likely to be found on in the interval x between 0 and L, right? It's not that it's not likely or never will be found for negative x values. It's just less likely. But be careful. Even though psi is twice as big in the positive x, that does not mean that it's twice as likely to be discovered on that side, because remember, probability is not psi. Probability is more like psi squared, right? All right. So yeah, so here is a bunch of physics. So I want to say one more thing though, really quick. So all of this is to answer the question, the following thing. So let me type it. What is the probability to find the particle between x1 and another value x2? Sorry, there. So the answer to this is the probability of discovering the particle between x1 and x2 is simply the integral from x1 up to x2 of the normalized psi star psi dx. This is an example of asking for some knowledge. And in particular, this is one of the things you're allowed to ask. And what I just showed you is how you ask it. And the interpretation is probability, right? That's all encapsulated here. Okay, so that's the lecture.